Howdy everyone, welcome to the Chapter 5 example problems. Here we're going to look over a couple common examples involving calorimetry, involving Hess's Law, and involving heats of formation that will come up a lot in the Chapter 5 problems you'll see. So, for the first one, it says here, this is a calorimetry problem. We have 5.10 grams of sodium hydroxide dissolved in 100 grams of water. The temperature rises from 20.5 to 33.2 degrees Celsius. They want us to calculate the heat in kilojoules and the delta H per mole of sodium hydroxide. Whenever it says just calculate the heat, remember that means we're just calculating Q, and then that one's going to be that. Now, the problem also did note that says assume this solution has the same specific heat as water, which means when we do our equation, that Q of our surroundings will equal the mass of the solution times the specific heat times the delta T. That this specific heat will be the 4.184 joules per mole, that's the same as pure water. So let's go ahead and plug that in. Our mass is the total mass of the solution, so not just the 100 grams of water, but also the 5.10 grams of sodium hydroxide. So that'll be 105.1, one decimal looks like, gram. Our specific heat, as we said, was 4.184 joules per gram degrees Celsius. And then our delta T, always final minus initial. So that looks like, 12.7 degrees Celsius. And so we'll just plug all that in and multiply it out. 105.1 times 4.184 times 12.7. Now you're going to get a large number, but if you notice, Celsius cancels out, gram cancels out. We're in joules here. So Q is equal to 5,580, let's see, we want 3 sig figs. So 5,580 joules, but they want that in kilojoules, so 5.58 kilojoules. And they did say in the question, it said how much heat is released. Remember, this is the surroundings, so the surroundings are a positive 5.58. The water absorbed that much heat, which means the Q of our system, how much heat did the actual process release, is negative 5.58 kilojoules. So that's our final answer. Sometimes that'll happen in the problem where they say how much is released. If that's the case, or if they say how much is absorbed, they don't care about the sign. They're just saying what's the magnitude. So for this problem, they probably actually want just 5.58 kilojoules. But if we're being very specific, we'd say, oh, the system had a change of negative 5.58. It released 5.58 kilojoules. All right, that was part A. Let's put that over there. That was A. Now for part B, they want to know what is that delta H per mole. Well, delta H is just the Q of our system, which we just found, divided by how many moles we use. So we got to find moles. So it's 5.10 grams of sodium hydroxide. So grams of sodium hydroxide on the bottom. We want moles of sodium hydroxide on the top. We add up the molar mass conveniently with 2 decimal places. It's 40.00. Very handy number to become familiar with. So 5.10 divided by 40. 3 sig figs, we have 0.128 moles of sodium hydroxide. So we plug that in, negative 5.58 kilojoules divided by, that goes up there, 0.128. If you wanted to, you could keep, the calculator's actual answer is 1275. You could keep 1275 there and then round after this step. It won't cause much of a difference and it would be within tolerance. All right, so 5.58 divided by 0.128, and we get negative, make sure you keep that negative, 40 3.6 kilojoules per mole, and that is our final answer there. Okay, so that's how you do calorimetry. If it's a bomb calorimetry problem, then the only difference is these two numbers, the specific heat and the mass, they're going to be combined into the calorimeter constant, because it's already taken care of. And so it's just, okay, those two numbers will be given to you as one. Do the same thing for the rest of it. But yeah, you always find Q first. Then if you need to find delta H, figure out your moles, combine it with your Q, get your kilojoules per mole. All right. For the next one, Hess's Law. I picked one that was a little bit more symbolic, but formulas are just symbolic, so it's all going to be the same. They give us some equations. They want us to find the delta H for this equation right here, where B plus C become 2D. So we've got to make these two equations combine to look like this one. So I always like to rewrite what I'm looking for. So B plus C goes to 2D. And then say delta H equals question marks. And then underneath it here, I'll say, well, let me rewrite these equations so that they will match up to this. So right away I see I need B and C as reactants. They're here in the first equation, but they're products. So I need to flip this equation around to make that work out. So I will have B plus C go to 2A. Because I wrote this reaction backwards, I'm going to flip the sign of the delta H. So that delta H is now negative 50 kilojoules. All right, for the next one, I want D to be a product, but I need two of them. And here I've only got one. So that tells me I need to double this equation. So it'll be 2A goes to 2D. And because I doubled that equation, I need to double the delta H. So it's no longer negative 80. It's now negative 160 kilojoules. And now it looks like I'm ready to add these up. So I'll add those and I'll add those. In this case, hey, 2A and 2A, they cross out. That's good. We get B plus C goes to 2D. And I add these up as well, so negative 50 and negative 160, so that's negative 210 kilojoules. And then I'll always do a double check to say, hey, did this equation I get at the bottom, does it match what I want at the top? Because sometimes when you combine things, this might have been like 2 plus 2 goes to 4, and oh, I got to divide everything by 2. I just double check to make sure it's the same. It is, so nope, that is my final answer. The delta H would be negative 210 kilojoules. All right, so that's how you do Hess's Law. Just don't get distracted by all this stuff. Just say, well, what needs to be a reactant? What needs to be a product? What do I do with my delta H if I should make any changes? Okay. Last one here, we're going to calculate the delta H of reaction. The book will often call this the standard enthalpy change, but that just means that the delta H of this reaction. Now, it does say in this problem you have to look up the heats of formation from Appendix C. So I'll put this here, Appendix C. So if you are a student who's still using an old copy of the custom textbook where it's just the first 10 chapters, you don't have Appendix C, which is really unfortunate. You need to open up your e-text on Mastering Chemistry and then find Appendix C there, way down at the bottom of the contents, or find the I can't remember if there a thing. I'm looking at it right now. No, there's a navigator. If you go to Table of Contents, you can find the appendixes pretty quickly there. All right, but I'm looking at those appendixes now, so I can look these up. But we're just going to find the heats of. Sorry about that. Lost track of which window I was using. Okay, just scrolling down to the phosphorus ones, or if you're in the textbook, flip forward to phosphorus. They're in alphabetical order by the name, not the symbol. So lead comes in before the M elements because it's lead, they're not going by PB. But anyway, we got to find these ones. Get my pen back. So we got to find PCl3. So that here is negative 319.6. We're going to find the POCl3. That is negative 542.2. And then oxygen's convenient. It's an element in its normal state. Oxygen's normally diatomic. It's normally a gas, which means the heat of formation is 0. We can skip that one nice and easy. Now these numbers were just the numbers. I did not multiply these by the balancing yet. So it's going to be 2 of those and 2 of those. So make sure you don't forget to check balancing. Now the equation that we want, the heat of reaction, is always equal to products minus the reactants. So we'll take this product number and say, okay, 542.2 times 2. So this will be, let me write it over here, equal to negative 1084.4 kilojoules minus, and then we put in our reactant, so it's negative 319.6 times 2. So minus a negative 639.2. And then we punch that in. So that number subtracted from the other number. And we get that our delta H of reaction is negative 445.2 kilojoules. I forgot my kilojoules there. The key thing is when it's minus a negative, it's same as adding a positive. So yeah, negative 1,000 plus 600. Yeah, negative 400 seems reasonable. Always kind of eyeball your answer to make sure that your answer seems reasonable about where you ended up. But that is the final one there. But it's always products minus reactants. Don't forget to multiply by your balancing. And always watch out for that minus and negative. You might minus positive. It all depends on what numbers you get. All right, so I hope that these examples help you for Chapter 5 for some of the common types. And I will see you back for Chapter 6. Have a good day.